Hi students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing the numericals of radiation. Take down please. A black body at a temperature of 1645 Kelvin has a wavelength corresponding to maximum emission of 1.78 microns maximum emission equal to 1.78 microns. Calculate the temperature of the moon if the moon is a black body if lambda m for moon is 14 microns. If lambda m for moon is 14 microns. I can use Vane's law of displacement. By Vane's law of displacement, I can say that delta m into t should be constant, in which case I can say that the constant value is 0.292898 into 10 raised to minus 2 meter Kelvin. Now once I have this, then I can say for a black body, here they've given you the temperature and the wavelength of black body. That means I need to calculate the constant. I don't take the universal constant. So I can say that delta m, that is for a black body, delta m is given to you as 1.78 microns, which is nothing but 1.78 into 10 raised to minus 6. Temperature is 1645 Kelvin. Therefore I can say delta m into t will give you the constant. Once you have the constant, then I can say for moon, delta m into t should give you the same constant. So in that case, the temperature of the moon will be constant upon delta m for the moon. Constant value you will find out from here. Substitute in the second equation, you should get your answer. The answer should be minus 64 degrees Celsius. Next, take on next one please. Calculate the value of solar constant. Calculate the value of solar constant if Stephen's constant is 5.7 into 10 raised to minus 8 SI units. Surface temperature of the sun is 5800 Kelvin. Radius of the sun is 7 into 10 raised to 8 meters, and the radius of Earth's orbit is 1.5 into 10 raised to 11 meters. Now I can say that the emissive power of the sun will be nothing but surface area of the sun, that is 4 pi r square, into the solar constant upon area 4 pi r square. So in that case I can say this is r upon r the whole square into s. Now I can also apply Stephen's law here. If I apply Stephen's law, by Stephen's law I can say that emissive power of the sun is equal to sigma T4 minus T04. Now I can say that where T and T0 are the temperature of Earth, Sun and Earth, T is temperature of Sun and T0 is temperature of Earth. But the temperature of Earth is extremely small as compared to that of the Sun. T is very big as compared to T0. Therefore, T0 raised to 4 will approximately be equal to 0. Hence, I can say that emissive power of the sun will be nothing but sigma T4, right? Now, once you have this, I can equate the first and the second equation. This is call this as first equation, call this as second equation. Both are emissive power, so I can say equating 1 and 2, I'll get r upon r the whole square into s is sigma T4, right? So in that case, you should get the value of s. S is the only unknown here. Should get your answer. The answer for this should be 1.405 into 10 raised to 3 watts per meter cube, meter square. Right? Take on next one, please. Calculate this. You can calculate that there, or you can equate it later and get the answer. Right? Generally in physics, guys, leave all the calculations to end. Otherwise, what will happen is you will have to calculate multiple number of times. Right? That will waste a lot of your time. This is a method where you can save a little time. Next, calculate the temperature of the sun. Calculate the temperature of the sun. If S is 1.34, if S is 1.34 kilowatts per meter square, the radius of the sun is 6.92 into 10 raised to 5 kilometers. And the distance of the sun from Earth is 1.5 into 10 raised to 8 kilometers. And Stephen's constant is 5.7 into 10 raised to minus 8 watts per meter square, Kelvin 4. Now, this is a replica of the previous sum. I'm not showing you the derivation again. I'll directly write the final formula. I've already derived the formula. So, all you can say, I'll directly write the formula so that we can finish the sum fast. I can say R upon R, the whole square into S is nothing but sigma T4. You should get your value of the temperature here. T is the only unknown in this. You should get the value of T. Answer for this should be 5492 degrees Celsius. That should be your temperature of the sun. Next, take on next one please. The amount of heat energy radiated by 1 meter square surface area of the sun by 1 meter square surface area of the sun per second is 6.333 into 10 raised to 7 joules. The distance between the center of the sun and the earth is 1.5 into 10 raised to 8 kilometers. And the radius of the sun is 6.9 into 10 raised to 5 kilometers. 6.9 into 10 raised to 5 kilometers. Calculate the solar constant. Emissive power of the sun I can say emissive power of the sun is nothing but 4 pi r square S upon 4 pi r square. Therefore, I can say that E is nothing but r upon r the whole square into S. Therefore, I could say S is equal to E into r upon r the whole square. That will give you your solar constant. Right? The answer for this sum should come out to 1.34 kilowatts per meter square. Next, take on the last sum, please. A black body at 0 degrees Celsius, a black body at 0 degrees Celsius radiates heat at the rate of 315 watts per meter square. How much heat is radiated in 1 minute? How much heat is radiated in 1 minute by a sphere of radius 10 centimeters at 1000 degrees Celsius, assume that the coefficient of emission of the sphere, is 0.8. Now I can say that for a black body, the emissive power, we'll call it as E1, is nothing but sigma T4. Next, similarly, I can say for a sphere, emissive power, we'll call this as E2, is E sigma T, we'll call this as T1, T2 raised to 4, right? Now T1 is given to you as 273 degree Kelvin and T2 is given to you as 1273 degree Kelvin, right? Now in that case, if I divide equation 1 and 2, this is 1, this is 2, divide 1 and 2, in which case I'll get E1 upon E2 is sigma T1 4 upon E times sigma T2 4, right? Sigma gets cancelled. So in that case, out of which E1 you know, E2 is the only unknown, you will come to know E2 from here. Once you come to know E2, then you can say that emissive power, you know, in that case you can say that heat emitted by the sphere is going to be H, which is nothing but emissive power into area into time, surface area 4 pi r square. So E2 into 4 pi r square into T. E2 I know, radius of the sphere I know, time I know. I should be able to get the answer for this, right? 1 minute was the time, you will have to convert this into seconds, so that will be 60 seconds, right? You should get the answer for this as 8.975 into 10 raised to 5 joules, right? Right, we'll stop this here for the day. Thank you very much.